Hello, my name is Giovanni Geraci. This is class number 9 of the course Signals and Systems 2 at Universitat Pompeu Fabra in Barcelona. If you have any questions on this class or any of the previous ones, feel free to get in touch via email or to check my webpage for more information about me. In the last couple classes, we learned the important relationship between convolution and multiplication in time domain and frequency domain. This allows us to study the behavior of LTI systems through their frequency response h of j omega. Today, we will first learn how to represent the frequency response of a system in terms of its magnitude and phase with the so-called Bode plots. Then we will focus on first order systems and we'll study the behavior of their impulse response, of their step response, and of their frequency response. We have seen that the frequency domain characterization of an LTI system in terms of its frequency response can be quite convenient because differential equations and convolution operations become algebraic operations in the frequency domain, so quite simpler. Since the Fourier transform and therefore the frequency response is in general a complex function, we need to represent it in terms of its real and imaginary components, or even better, in terms of its magnitude and phase. So if the Fourier transform is a complex function of omega, and we write it as x of j omega equal to the magnitude of x of j omega times e to j the phase of x of j omega, then the magnitude describes the frequency content of a certain signal, right? Let's say how much energy lies at each different frequency. And the phase describes the relative phase of these complex exponentials that compose our signal. So for an LTI system, the Fourier transform of the output y of j omega can be obtained as the product between the frequency response h of j omega and x of j omega, which is the Fourier transform of the input. So the role played by h of j omega is then clear. The magnitude of h of j omega scales the magnitude of the Fourier transform of the input, and the phase of h of j omega introduces a phase shift on the Fourier transform of the input. We should notice that a linear phase shift corresponds to a simple delay, so it does not introduce any distortion. Let's see an example. If our h of j omega is e to minus j omega t0, then the magnitude is obviously simply 1 and the phase is minus omega t0. So this is a linear phase shift, linear in the variable omega. And if we anti-transform, in the time domain, it corresponds to an impulse response h of t given simply by delta of t minus t0, which means that for a given input, we obtain, for a given input x of t, we obtain an output simply given by x of t minus t0. On the other hand, a non-linear phase will cause distortion of the signal. So again, the linear phase simply corresponds to a delay by a certain value t0 in our example. A non-linear phase will cause a distortion, not a simple delay. Distortion means that the shape of the signal will be completely altered. We can see an example in the figures at the bottom of this slide. Imagine you have an original signal like the one depicted at the bottom left. Then if you apply a linear phase shift or a delay in the time domain, then the signal in this case is simply delayed by time 10. If you apply a nonlinear phase instead, then a distortion is caused and the shape of the impulse is completely different. When displaying graphically a Fourier transform, particularly the frequency response of a system, it is often convenient to use a logarithmic scale. Um, this can be done through the so-called Bode plots. Let's see why and how. So plotting the magnitude of the Fourier transform in logarithmic scale has several advantages. So when we use logarithmic scale, then we can span a wider range of frequencies omega, and we can also highlight values in the stop band. What does that mean? It means that usually if you, for example, have a filter, then the frequency response will be approximately 0 in the stop band. It would not quite be 0, but it would be very small. If we display this value in linear units, then it would be difficult to appreciate the attenuation provided by such filter in the stop band. But if we do it in logarithmic units, then it will be much clearer how much the attenuation is. Another advantage is that imagine you have a system with frequency response h, a signal x goes through the system, and then there's an output y. Then through a logarithmic representation, the log of the magnitude of the Fourier transform of the output y simply is obtained as the sum in logarithmic units of the magnitude of the frequency response and the magnitude of the input. Typically, when doing such a representation, we use a scale given by 20 log 10. It means that we calculate the logarithm in base 10 of whatever quantity we want to represent. In this case, it will be the magnitude of a Fourier transform, and we multiply by 20. This scale is also called decibels or dB. So by using such scale, a unitary gain corresponds to 0 dB, and a gain of 10 corresponds to 20 dB. Conversely, a gain of 0.1 or dividing the magnitude by 10 corresponds to subtracting 20 dB, and a gain of 2 corresponds roughly to 6 dB. So if we look at the figures at the bottom of this slide, we have a representation in logarithmic scale for the magnitude of a Fourier transform on the left and the phase of a Fourier transform on the right. So you see that in both cases, the x-axis is in logarithmic scale. So we go from omega equal to 10 to omega equal to 100 and then 1000. And in the case of the magnitude, also the y-axis is in logarithmic scale to appreciate the value of the magnitude. And we clearly see that when this frequency response attenuates for high frequencies, we can precisely tell by how much. In a previous class, we introduced LTI systems described by linear constant coefficient differential equations. These are of great importance in practice because they can model many physical systems and because such systems can be easily implemented actually. The order of such system is given by the highest derivative in the equation that describes it, and higher order systems are often obtained by combining systems of the first and second order. So since first order and second order systems play such an important role, we will now study the behavior of first order systems. In the next class, we will focus on second order systems. So let's take a first order system, which is described by a differential equation tau derivative of y of t in dt plus y of t equal x of t, where tau is a positive number. We can easily calculate the frequency and then the impulse response of such system. How? If, for example, as we learned in a previous class, we calculate Fourier transform of the left and right hand sides of this differential equation, then the derivative becomes a product by j omega, and then we can just calculate h of j omega as y over x. We obtain this ratio of polynomials of the first order given by 1 divided by j omega tau plus 1. And we know that this Fourier transform has a well-known anti-transform, which would be given by h of t equal 1 over tau e to minus t over tau u of t. So it's a right-sided decaying exponential, as you see represented at the bottom left of this slide. Once we know the impulse response, it's also possible to calculate the step response of such first order system by doing the convolution between the impulse response and a step. And doing such convolution produces a step response s of t given by 1 minus e2 minus t over tau u of t. And we see this represented at the bottom right of this slide. So what can we say about first order systems? In terms of impulse response, so the response to an impulse is basically a sort of step that then decays, okay? Whereas, so we see the spike, the system responds to an impulse with a spike, and then such spike decreases, goes to zero, not instantly, it takes some time. Cool. Something similar happens for the response to a step. If we give a step as an input to the system, then the response s of t is something that looks like a step. It's a signal that eventually converges to 1, but it takes some time. It doesn't go up from 0 to 1 instantly like the step. Right, so we notice from these figures that the smaller the value of t, the faster the response of the system. Yeah, because for the impulse response, a smaller tau corresponds to a response h of t that decays faster, and also it has a higher peak because the maximum value is 1 over tau. Similar thing happens for the step response, because a smaller value of tau means that the value 1 minus 1 over e is reached faster, is reached sooner. That means that the step goes up faster, and therefore it approaches the value of 1, which is the final value, faster. So we can now calculate the magnitude of the frequency response and try to represent it in a way that we just learned, so through a logarithmic scale. To do that, we calculate 20 times the logarithm in base 10 of the magnitude of the frequency response h of j omega. Such frequency response, we've seen, is given by 1 over j omega tau plus 1. So through some simple manipulations, we first calculate the magnitude of such fraction. We obtain 1 over the square root of the square of the real part plus the square of the imaginary part. And then we notice that the square root inside the log contributes a factor 1/2 outside the log, and the fact that it's at the denominator contributes a factor -1 outside of the log. So long story short, in the end we obtain minus 10 log 10 of 1 plus omega tau everything squared. To represent this, it is quite helpful to look at the asymptotic behavior of such equation. So what we do next is we study that formula for omega much smaller than 1 over tau, and for omega much larger than 1 over tau, and we find something quite simple. So when omega is much smaller than 1 over tau, then the term inside the log is given by 1 plus omega tau square, and such omega tau square is much smaller than 1. It can be neglected, therefore we can approximate the whole thing by 20 log 10 magnitude of h of j omega equal to minus 10 log 10 of 1, which is 0, it's 0 dB. So in the end we have that for omega much smaller than 1 over tau, the magnitude of frequency response can be approximated by 0 dB. In the other case, the opposite case, when omega is much larger than 1 over tau, well, we have that omega tau square is much larger than 1. So inside the log, the factor 1 can be neglected. So we can approximate everything by minus 20 log 10 omega tau, which is also rewritten as minus 20 log 10 omega minus 20 log 10 tau. Right, so once we know that, we can attempt sketching the magnitude of the frequency response with a Bode plot in a logarithmic scale. Let's do that. So first of all, let's look at the figure at the bottom right. Let's look at the dashed lines. So these two dashed lines represent some asymptotic approximation through the two values that I have just explained. So the first one, for omega smaller than 1 over tau, is a straight line at 0 dB, because we saw that 0 was a very good approximation in that regime. However, in the other regime, when omega is larger than 1 over tau, much larger than that, a good approximation is given by minus 2n log 10 omega minus 2n log 10 tau. So it's a straight line which decays by 2n dB per decade. It means that if omega grows by a factor of 10, the value of the response decays by 20 in a dB scale, right? And that's what we see there. This is just an asymptotic approximation. If we wanted to calculate the exact value, so not the approximated one, then we would look closely at what happens for omega equal to 1 over tau, which is called the break frequency. And we will see that by replacing omega equal 1 over tau in the original formula, then we would obtain minus 10 log 10 of what? 1 plus 1. And we know that that corresponds to minus 3 dB. So the actual value for omega equal 1 over tau is not 0, as our asymptotic approximation says, but it's actually minus 3 dB. However, we see the approximation, which we obtained very easily, is quite accurate. It tells us a lot about the behavior of the system. Notice that the smaller the value of tau for such first order system, the larger the break frequency, omega, meaning the larger the value of omega after which the system starts attenuating. So before that value in the figure, before the value 1 over tau, for frequencies smaller than that, the system basically has a unitary gain. It doesn't attenuate. But then as omega grows beyond that break frequency, 1 over tau, then the system starts attenuating, and it attenuates quite a bit. We can also study the phase of the frequency response. So if you go back and look at the expression for the frequency response, you see that the phase can be written as minus arctangent of omega tau. And in this case too, we can have some very simple approximations that are going to help us in sketching the phase of the frequency response. So again, when omega is much smaller than 1 over tau, for example, omega is smaller than 0.1 over tau, what happens? Well, omega is much smaller than 1 over tau, then minus arctan of omega tau can be approximated by 0. On the other hand, when omega is much larger than 1 over tau, well, this quantity can be approximated by minus half pi. Why is that the case? We can see the same thing differently. So if omega is much smaller than 1 over tau, then omega tau is much smaller than 1. So it is a number very close to 0. So that means that the corresponding value of the arctangent of that number is 0. On the other hand, when omega is much larger than 1 over tau, then it means that omega tau is much larger than 1. And therefore, the arctangent of that value, which approaches infinity, is half pi. And because of the minus sign, we get minus half pi. There are different ways of seeing this, but the message here is that by using these simple asymptotic approximations, well, we can quite easily sketch in this case, the phase of the frequency response. So let's do that. So if I use the asymptotic approximation to the left of 1 over tau and to the right of 1 over tau, let's look at the figure. I obtain a straight line and another straight line. In this case, in between those values, so between 0.1 over tau and 10 over tau, it is good to have a linear approximation. So again, for omega between 0.1 over tau and 10 over tau, we can use a linear approximation. What would be the exact value at the break frequency, which again is 1 over tau? Well, if we replace the value omega equal 1 over tau, back up in the formula of the phase of the frequency response, we will get minus arctangent of 1, which will give us minus pi over 4. So that would be the exact value. So let's look at the figure again to check what we have just said. The dashed line is the asymptotic approximation. We use the two asymptotic values to the left of 0.1 over tau and to the right of 10 over tau. It's two horizontal straight lines. The first one has the value of 0 and the second one has the value minus half pi. In between, we said it's good to use a linear approximation. So we just basically connect those two straight lines with a diagonal line. That's our linear approximation in between. The solid line on this figure represents the exact phase of the frequency response, and you see it's pretty close to the approximated one, and it's exact at the break frequency. At the break frequency, the value is minus pi over 4, both for the approximation that we have used and for the actual phase. So the exact value matches with the approximation. So today we first learn how to represent the frequency response of a system in terms of its magnitude and phase. So we learn the so-called Bode plots. Then we focus on a first order system and we study the behavior of the impulse response, of the step response, and of the frequency response of such first order system, both its magnitude and phase, and we learn how to represent it. In the next class, we will extend our study to systems of the second order. So see you in the next video.